Okay. So let's get started. Today will be the last topic that will be covered in the final exam. Um, so this called a federated learning is basically coming out like quite recently, like probably after like reinforcement learning. Um, so when you do all of the learning, right? Everything happen in the same machine, right? Your data in your computer and your CPU, your GPU would be in the same computer, right? So that is a traditional way of training a machine learning model. So today we are exploring the possibility of combining processing power from different machines. And to do that, we'll start with first the motivation, right? Why why do we care about pooling the resources from multiple devices? So right now, our data is not in one place, right? Your computer have data, your lab have data, right? So everyone have their own data, right? Everyone take a photos, and the photo in your library in your phone is also a data set, right? That can be used for training, like computer vision application. But the hard part is that, well, we have all this data, but it's very difficult to combine all the data together, right? If you have 10 people, you need to have a centralized server. Everyone upload their photos into the centralized server before you can start training the model, right? And if you have maybe 10 million people, it's going to be almost impossible to upload all of them at just one place. So how can we still perform a machine learning algorithm, but the data is spread across multiple devices? Can we actually learn something remotely, right? That is our challenge. So centralized setting is actually a key because, well, if you want to send a data, right, there could be a cost of sending data. Everything is not free. It can cost maybe your bandwidth, right? When you upload, you need to take a portion of your internet, and that could also take time, right? Some data can be sensitive. For example, if you want to make an application to analyze the CT scan image, then each hospital would have their own data, right? Would have their own CT scan images, but you cannot just send all those scan images into one place because there are a protection on the data, right? It's the patient's privacy. You cannot send someone else, CT scan to a third party, right? So we have something called uh, PDPA. Is the law that put a protection on the data, right? If you own the data, the hospital cannot send your data out elsewhere. So these are some of the issues when you want to do a centralized machine learning. So up until now, when you want to perform a machine learning, you have to look for a benchmark data set, right? Someone make the data set available for everyone else, and then we use it. But there are a lot of specialized problems that you actually need a specialized set of uh, data, and that data is protected by this law. I mean, it's a good law to protect your privacy, but for machine learning perspective, it actually prevent us from learning uh, a large variety of data. So how can we handle all of these issues. So the solution that they come up with is using a federated learning. And this word is not a new learning algorithm. So the learning part, you still would use the supervised, unsupervised, so that are the same. But federated learning is about setting up how you distributed the learning part and also the data. So federated learning is actually a setting, right? It's basically a setup or an architecture of the learning. And the premise is that you can have multiple clients, right? So each device in your environment will be called client. And this client will try to collaborate with each other to solve a single machine learning problem. And each client will have a raw data stored locally. And it's not exchanged or transferred, right? So the data is in place. One client cannot see the data of another client. Even the server who actually communicate with each client can also not be able to see the data. So what can be exchanged between client and server? So there are many ways of actually exchanging information. So one would be the update, right? So what is the update? So when you are performing machine learning, right, you are not solving optimization problem, but you are actually trying to move your model into the optimal model. So whenever you perform maybe one batch of evaluation, you would have some gradient that you would update to the current model, right? So normally when we perform all this type of learning, you have, we have the same model, the same parameter would be equal to the parameter plus some learning rate times the gradient, right? So because the data cannot be exchanged, but we can still exchange this part. So instead of updating each one of them individually, you can send this update into a centralized server, and the server will take into account all these updates from different type of data set and combine them into a new update function for the center model. So that is the structure of the learning. So let's look at some of the example, right? So we have a server, right? We have the server. Now the server here is just a controller. There's no data in the server. And then we have all these clients, right? All of these clients. And the client have data, right? So at the start, right? At the start, what we do is we initialize the model, right? We have a machine learning model. Maybe we create a neural network. And this model is actually the same in every device. What do we mean by the same? It's the same structure. It doesn't have to be the same initialization weight, right? As long as they have the same structure, it will work. So each of them will have their own model and their own weight. And then we train, right? Each of the model will train on the data that they have, right? Each of them will train on the data that they have. And after they finish the training, they send the weight right? So because you cannot send the data, you can send the weight instead, right? And some people will say like, okay, because the weight learned from the data, maybe it still have some data containing it, but in some point of view, we would think that well, the weight is independent of the data. It's not actually the data. So you are also you can send it to a third party. So each of the model, each of the client will send back the weight into the central control, and then the control will figure out a way to combine, right? You have this model, you have to find a way to combine them. And the reason that we want to combine them is because well, each one of them, right, each client will have a different distribution of the data, right? For example, if you want to classify between cat and dog, right, a classic example, maybe the first device have a lot of cat photo because they have cat as a pet. The second client would have dog as a pet, so they have more dogs, right? So each of these model will be good to classify each of the two, right? So they have to find a way to actually combine all of this effort for each device that is trained. And after they combine, they send back, right? They send back the same model that they combine back to the client. And this process will continue, right? So after you send back um, the weight to the device will train again. But the initialization would be using this weight, but using to train the same data, right? So they are back and forth interaction between the centralized server and all these clients. So that is the heart of the federated learning, right? And right now, there are many researches that done using federated learning. Um, they would try on a different data set and check if the model will convert faster if you would train on, like if you split the data set into smaller chunks for each of the device, or you just combine them into one big data and then just train in one machine, right? So there is still no clear cut whether or not setting up this way would perform better than just having all the data in one place, right? So there are some um, discrepancy between the two learning paradigm. And in in mathematical sense, there is no proof that you would attain the optimal model using the federated learning. But the application for it, right, is to be able to use the machine learning on each of the device to help to help with the big tasks, right? So because right now every phone have a chip with AI, right? So they are capable of training on its own, and it would be easier for us to share the weight instead of the data. So that would be, a way to the future. So imagine with your phone, you have the AI model for image classification, but as you take more photo, like your model will keep improving. And then when you walk past by someone else, right, your phone and their phone will have may have the interaction, may exchange the weight just by walking past. And you can improve that by just exchanging the weight, right? So that is one way, but there's no guarantee that it's going to improve, but this is a way to learn. So that is the key ideas for federated learning. There is another word called distributed learning, and there is a distinction between federated learning and distributed learning. In federated learning, the data is separated into multiple devices, and the data is not shared. It is non-ID, which means that it can be very biased, right? And be imbalanced. But for distributed learning, so the word distributed means that your data is still in one place, but you have multiple CPU, multiple GPU that would help training on the same pool of data, right? So that is the aim is to train faster, right? So you think of it as a parallel, right? Um, you want to train machine learning, but you want to train in parallel, right? That is what distributed learning means. But for federated learning, the aim is just to train with constricted regulation. So that is the distinction between federated learning and distributed learning. So what challenge that FL federated learning try to solve, right? The first would be the data privacy. Because the data is not shared, you are actually not leaking any information from uh, from your own device. And for the communication, you only need to exchange the weight, and the weight is actually much smaller than the data itself, right? For example, you have one image. How much? What is the size of a regular image? It's probably 1 MB to 2 MB on average, right? And when you have the machine learning model, the number of parameters is your size of the model. And typically, you would have about 2 to 50 million parameters, right? The one that are very small would be like 2 million parameters. For large language model, you would have up to like 50 million um, parameters. And each parameter is one number, so it's occupy 1 MB, one byte. So the model would take about 2 to 50 megabytes. So it's equivalent to about 25 or 50 photos. So that would be faster than just sending the data itself. There are more challenges that we still have to solve, right? So we solve this too, but the rate is still difficult, right? For example, what if we have malicious parties? So what is malicious party? Right? So when you are trying to communicate with multiple devices, they you are not guaranteed to get the result from those devices, because each device would have different hardware, different software, and it can have a failure, right? It can, maybe one of them doesn't train correctly, or maybe some of them just have some malfunction, and there's no way to tell um, what device is experiencing this difficulty, right? If you have, for example, a hacker or someone who is like want to destroy the system, they can just use the model with just random weight and then try to send this random weight without training to the server to just make the server confused, right? So there's no a clear way how to combat that. So we have many forms of federated learning. Um, the first form is called cross-device. Um, for cross-device, you have a massive number of clients, right? Up to 1 billion clients. And each client will have a small data set, right? It can be as low as just one data. And the challenge for this type of federated learning is that you need to make sure that you have a way to communicate to all of them, right? So remember, we are still capped by the bandwidth, right? The bandwidth of your internet, right? If you have 1 billion devices, each device sending the weight for like maybe 2 megabytes, then you are looking at like a terabyte of data per one transfer. So in this particular setup, you would not try to communicate with all of the devices at the same time. You would have some randomized way of choosing a subset of of the devices and then tell them to train. And then when you get the weight back, you update your weight, and then you pick a new subset of uh, devices, and then you let them train. So that would be a way to combat the availability, because you cannot be sure that all the devices will be online at the same time. The second form is called cross-silo federated learning. Now, in the cross-silo setup, your client is actually maybe a bigger client, right? It's more reliable. It contains a larger data set, right? So you can think of this as maybe one hospital, like each of these would be one hospital, and each hospital would create their own machine learning model, and then each one of them will share the model to the central server, and the central server will do the update together. So in this setup, it's actually more costly because each of the party would need to be online almost all the time. But the benefit you get is like each one of them would be pretty quite accurate because they have a large data set compared to the cross device. The third form is called server orchestrated federated learning. In this way, we have a client server communication, and the server is a single point of failure. So the server will tell which device would need to be trained, and after it tells the device to be trained, it extracts the weight from that device, and then they try to combine the weight from multiple devices, and then they just try to tell the client in the new iteration to retrain. So in this sense, you would need the central server to be able to control the client, right? It's a little bit different from the cross device, because in cross device, each of these device would always be training on its own. And whenever it comes into contact with the server, it will send the weight. But in the server orchestrated sense, the server will tell each device which to train, when to train. So device on its own will not do the training at all when it's not online, right? So that is one of the distinction. And then we have a fully decentralized federated learning. So we can think of it as a peer-to-peer, like a peer-to-peer connection, right? Basically, there's no server, but each device will communicate it with a nearby device. So in this sense, each device would always be training on its own. And when it comes into contact with a neighboring device, it will exchange the weight. So the weight will be exchanged in two ways, right? So you send the weight into this device, and then this device will send the weight back. And because there's no centralized server, right? Each device would have a different weight. Will always have a different weight, right? Because if two devices never met each other before, right? Of the exchange that they have would never occur before. So they would not have the same weight, right? So in the fully decentralized setup, you can scale infinitely, right? You can always scale because you don't need a server, you don't need someone to help combining all the update for you. But the challenge would be how would you update, right? Because at some point, you will be you'll be in contact with maybe some of the devices, and you would combine them the same way as the central does, or you would try to do something different. So these are the four forms of federated learning. You can have multiple setup. Sometimes you would try uh, of them and then compare which one would perform better in some data set. So now we are diving into the algorithm part, right? So I told you that in the server client setup, right? The server get the weight from the client and they want to combine, right? But I haven't tell you how to combine. So we need to have some algorithm to combine all the weight together. So our setup would be we have a set of K clients, right? So we have the centralized server, and then we have this small client, right? So the client have their own data, right? D1, D2, D3, DK. And what we actually want to do, we want to minimize the objective function. And the objective function for every data, right? So this is the objective function for if you combine all of this into one big data, that will be what you want to optimize, right? So f is your loss function, right? This is your loss function. But because you don't have the data in one place, you have to break this apart into a smaller loss function. So that's why we have the summation here, right, from 1 to k. So the summation tell me that, okay, the data is in different places. So we want to compute the loss in each place separately. So the loss in each of the clients is this one, right? So we have the loss function for the device K, and that will be for the dataset K. And when we want to optimize this objective function, we have to take into a consideration that each device is not equal, right? Some device would be better than the other, and the way to there are actually many ways to actually identify which device would be better than each other, but in general, you would look at the number of data that they have, right? The more data they have, the more reliable they are. So when you compute the cumulative loss function, the weight in front, right, this part, would be based on the number of data set. So n is the total number of data, and then n subscript k is the number of data for that device. So we break down the loss function of our centralized setting into a federated learning setting. And so when we have uh, the objective function, we can try to minimize each of the device at the same time. So we start from the right side first. So we have the client update. This client update will be performed on the client, right? So we have a batch size, we have the number of local steps, and then we have the learning rate. So these are the parameters for your client. And for the client, right, they will do 1 to L iteration. And in each iteration, they will sample the data from their dataset into a batch, right? So we have, we say the batch size would be 32. If they have 100, it's gonna sample randomly 32 example from 100 images. And then what do we have? We have, we update the weight, right? Using the gradient of the loss function. So when you update the weight of the client, you send this weight into the server, right? So that is what the update function does. So once each client finishes the update, they will send the weight into the central server. So now is the time for the central server to combine them, right? So we look at the server side algorithm. So for the server side algorithm, right, they would also have a loop, right? Each round. And in each round, they will select a random set of clients, right? So not all clients participated in the update at the same time. So this subset of a client, right? They will do the client update at the same time, and each client will send back the parameter of that client. And because we set up our objective function with this weight, we will use the same weight when you update your main parameters, right? So normally you would sum up all of the weight from the client, but the way that you sum it, you weighted sum, and the weight will be based on the size of the data. Right, so so it is basically a weighted average of the parameters from the client. Right, so this one way that you could do, right? This one is called share weight. right? Share weight principle. You can also share the loss function as well, right? So instead of updating the weight for the client, you can send this back to the server, and the server will also do the same using this equation the same way, but they will do the sum for of the client instead. So if you share this one, it's gonna be called share gradient, right? So you can share weight or you can share gradient. So what about fully decentralized server, right? So this algorithm is for the first three setup when you still have the central server that communicated with the client. But what about this one, right? There's no central, so like you don't have the code for server side, you don't have the code for client side. So we have to do something a little bit different, right? So for the central decentralized setting, you view it as a graph, right? So we have the device as a node, and then the connection between devices would be edges of the graph, right? So by defining it this way, you can construct the graph of the decentralized setup, and the graph can be embedded into the adjacency matrix. So adjacency matrix is just a representation of a graph, right? For example, you have like a graph like this, A, B, C, D, right? When you write into a matrix, right? So you would have A, B, C, D on this side, and then A, B, C, D on the column and on the row. And if there are edges between them, for example, there are edges from A to D, which means that A can communicate with D, then you would put one here, right? And then we have A to B, A to B, and then we have C to D, right? And then we have B to C, right? And then everything else will be zero, right? So this is called the adjacency matrix, right? So basically you put zero when there is no communication between two devices, and then you put one in for um, a communication between the two devices. And we have a model for each of the device, right? The same way, from 1 to k. And for each party, this W, right, time weight is the aggregation among the neighboring nodes. So what it mean by this is that basically you only look at your neighborhood, right? If you have your weight, right, you have your weight like theta 1 into theta k over here, right? When you do the multiplication, you would do row multiplied by the column, right? So for each of the device, right, you will have this row multiplying with each column, right? And each column would be the different weight for each of the device. And this 0, 1 will be basically tell you which weight of which device will be added into uh your own weight. And so the algorithm for fully decentralized algorithm would be you only have one algorithm for all the device, and what you do is you would try to look at so this one is what you trained, right? This is for yourself, right? So this is what you train for yourself, right? You update the weight based on the data that you have, and then this is update, right, from neighborhood, right? So in one iteration, you do two updates, right? One is updating for yourself. Another one is updating using your neighborhood weight. So so one thing to notice is that in the first update, right, you add a small you have this learning rate, right? So you add a small gradient into your weight, but for the second time, you just take all the weight of your neighborhood with yourself included. You compute the weighted sum, right? You have the weight for here, right? So this is your matrix, right? And then you try to combine the weight. So that is for peer-to-peer, right? So for peer-to-peer, you do two at the same time. So in some setup, right, between these two lines, like between these two lines, you might want to wait. You might want to wait for your neighbor to finish training before you can actually combine the weight together, right? Because sometimes you would train faster than your neighborhood. You still have to wait. So that is the algorithm for fully decentralized setup. So how many clients is good, right? How many clients is good? Like is it a lot of client is good or small client is good? So we have what we call a cohort size. The cohort size is basically the number of participating client at every communication. So in the centralized sense, right, you are picking a random set of your client. So not all of the client is participating in the update at the same time, right? Only some of them. So how you pick how many to participate in one iteration? So what we learned, right? So they try the number of participation rate and they test it with the test accuracy. So what do you mean by participation rate? So if it's one, it means that if you have 100 devices, at each iteration, only one device will be participated in the update. And it's clear that the more participation you have, you would get a better accuracy. But at some point, right, at some point, you would, on this one is trained, right? For the test, right, at some point, sometimes you would drop off or there's small improvement. So there are a certain threshold that you can push for to obtain the maximum efficiency compared to the accuracy, right? So to actually pick the cohort size before training is very difficult, right? There is no formula or no like rule of thumb how many devices you have to pick for the participating. And in all of the federated learning papers, you would have to include this diagram, right? You have to change your participation rate and see what is your accuracy. And there's a trade-off, right? So you can always increase the participation rate to maybe like 80%, 90%. But there's also a cost associated with it, because the more the more client in the participation, you would have to pay a lot more for the data communication cost, right? So that is one of the trade-off that you have to pick. So it's quite similar when you look at the start, right? When we do the clustering, and we don't know which K to pick, so we pick multiple K, and then you plot the graph, right? And then you look at some of the cut point that you can think of that it would be the best fit. So this is kind of like similar to that, right? There's no formula for K for K mean, so there's no formula for cohort size in federated learning. So the client selection, right? So in the algorithm before, right, we pick the client at random, right? It at random. And that could be fine in a perfect setting when all the client is online at the same time, right? But sometimes when you request the client to send the weight, maybe that client is offline, so you cannot get the weight. You have to try to send another one that you haven't picked, right? So if you pick it at random, well, you get some performance, but because the way that you combine the weight, right? When you combine the weight, you use the size, right? You use the data size as part of the weight, right? So it means that you put more emphasis on the device that have a larger data set. So perhaps we can put some weight when you select a client, right? So not only that we have this weight, right? We have this weight for the update. Maybe in the random here, we also use this weight to pick at random. So the device with a larger data set would be more likely to be picked at each iteration compared to the device with low uh, lower data set. So that is also another one to be considered. So the client selection problem is also um, another axis for federated learning, right? Because if you select um, very strategically, it will lead to a faster convergence and reduce the communication cost. So in the graph here, right, when they pick the cohort size, they pick at random, right? They pick at random, like uniformly random. But if you change your strategy, maybe you might convert faster, right? So for example, like until you reach that point, maybe you only need the participation to be at 1%, right? Or maybe 5%, right? Faster convergence rate. But it doesn't improve the accuracy, right? The accuracy would be roughly the same. It's just that it reach the convergence faster. So what are the approach for selecting the client? The first one is called loss-based sample, right? The loss-based sample. And we pick the client with a high loss value, right? High loss value. So why do we want to pick a client with a high loss value? Well, we still say that it's simple, right? Because when each device trained, right, they have a loss value of their own, right? And then they would update the weight of their own. And based on the loss value, so this loss value doesn't um, doesn't depend so much on the size of the data set, right? The loss value would be similar. So the good thing is it's quite simple because you already compute this value in the client. So basically, when the client send you the update, they can also send you the loss value because it's already computed. And then you can use this loss value to do the selection, right? So that we have the loss band sampling. We have the sample size based sampling. So this is what I mentioned previously. So the client with larger number of data sets, you would pick it more often than the others. Another one is called similarity-based sampling. So the similarity-based sampling is that you want to pick a diverse set of parameters, and we can try to compare two weight from two devices, and if the weight from two devices are very similar, then maybe you only need to pick one, right? If you have something similar for multiple devices, there's no need to get multiple copy of it. You only need one copy. So you want to select a diverse client based on the gradient, right? For example, you have the gradient in each direction, you would pick maybe you would pick like this one, and this one, right? And because this one is very close to this gradient, maybe you don't pick. And because it is a similarity based, right? You have to provide a function to compute the similarity. And if you want to compare the gradient, what should be the best function for similarity? What what do you think? So we learned from clustering, right? We have that similarity measurement, right? So would Euclidean distance would be best for gradient, right? For gradient, what we care is the direction of the gradient, right? You want a diverse direction, and when you compare direction, you want to compare the angle, right? And the only similarity function that compute the angle for you is called the cosine similarity function, right? So if you want to use the similarity base, you use the cosine similarity function to compare two gradient, right? It's going to give you the angle between them, and then you want to make sure that the angle is far apart for the entire cohort that you pick. right? So these are some of the kind selection approaches. There are more to learn. As you can see, right, a lot of information from this slide is from 2021 onward. So it's quite recent, right, in the past 4 or 5 years. So the federated learning is still fresh compared to other type of learning, and it could be the future of learning because the edge device, the smaller device, become more and more powerful. Basically, your phone have this all this AI device, and it can be able to communicate with each other, maybe via some form of like a Bluetooth. So the technology is here, but whether or not the phone company or the application company would utilize this is still in question. But the selling point for the federated learning is the privacy of data, which like one of the most uh, important aspect when you want to use a service or when you want to use uh, um, the machine, right? Because when you subscribe to a service, mostly you don't want it to send the data elsewhere. But I think in the future there will be like a checkpoint, like if you want to send the data to third party or you want to send the machine learning model to a third party. And in often time, right, if you send the weight, it's basically after all these calculations, right? When you train the model, all these calculation is becoming um, the the learning part, and the trace of the original data is gone because now you have this knowledge embedded into the machine learning structure. So this is not your data, so you can share it with everyone else. Just like when we share the pre-trained model, right? Because in the pre-trained model, you train on data set, right? But in most of the pre-trained model, they train on the data set that are publicly available. So there's no privacy issue because they already decide that your data will be publicized. So that is the federated learning, right? There's not a lot to talk about because it's quite new. But if you are interested in machine learning, maybe you want to look at the federated learning for the future. So that's it for this class. It's very brief. Uh, so hopefully you learn something about machine learning in this after you finish this course. Don't forget to finish your last assignment before March 26th. And we have the final exam next week, the same usual time, but 30 minutes earlier, basically from 8:30 to 11:30. The format will be the same as the midterm, right? So you know the drill. If you want to bring the material, it has to be in the physical format. Any question? Yes, we will cover everything after the midterm. I think there are more topics than the midterm, right? Yeah. So that there will be more topic cover. Yes. Yeah. Yeah. You can send send message to me. You can share the if you use Colab or Kaggle, you can share the notebook so I can look into the code. If you use Jupyter Notebook on your local machine, you can also send me the Python file. Okay. So yeah, so there's no question. Then we'll see you next week for the last time. Okay. Thank you. Oh yeah, 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 yeah. Yeah, yeah, I remember.